Hello. Thanks for having me. Thanks for the audience for sticking around. In work for me, it's a late afternoon. Okay. So to orient the audience about what this talk is about, because I put it together just for this conference. I'm going to try to making an overarching theme, which is that I think when discussing methodology and statistics, we should be taking the math less literally and taking researchers more seriously. I don't have a paper, a blog post on this. This idea is built on having like a punchline out of 3 separate projects. One that I'm working on, and I'll talk the most about, which is on applying mixed models to psychology experiments. Then a couple of papers and blog posts on meta-analysis, which I may have to skip, and a very quick thought on Bayes factors. Now I'm trained as both an economist and a psychologist, but most of my research has been on psychology. So most of my thinking about methodology is tinted and most relevant for that. But I think there are some lessons that can be exported to other fields. Okay, so from my perspective, I think of myself as a methodologist. I'm definitely not a statistician, but I've done a bunch of projects on methodology. I think of us as having, in this role, a supporting role. So I think of John Baptiste, that's us. And we don't have the value on our own. We derive the value from what we do, from what researchers do, what we do. So you can think of Colbert as the actual researchers. I realize John Baptiste is a very successful musician who's actually no longer at the show, but he makes the point that the show continues without him. And that's the way I think of our role with researchers. So when I'm not doing methodology, I'm doing judgment decision-making, which combines psychology and economics. And when I write papers and I read papers, I worry that we study things that are interesting about decision-making, but maybe not important or not useful for real decision-making out in the world. And as a methodologist, I have a very similar concern that we may study things that are interesting to us from a mathematical or philosophical perspective, but that may not be that useful for people who are using our research. But I struggle with this a bit more in my role as a methodologist. Because when I think of decision-making, if I think of MBA students, and if we're doing something that may be considered silly, for example, in psychology a few years ago, there was a big fad on embodied cognition where, without getting into too much detail, the idea would be that if something happens to us in our bodies, we experience something like we hold a warm cup of coffee, then it's through the metaphors we associate with those experiences, it influences how we perceive or think. So we associate warm with being prosocial. So just holding hot coffee, we may be more prosocial. And there's a lot of papers, maybe 20, 50 papers on this. And so let's say this is, I think you can see my mouse, if this is not useful, and I tell it to a person in the real world, they can judge for themselves whether holding a cup of coffee and making you more prosocial, if that's important or not. But the researchers have a hard time deciding whether, when we think about random effects, if that is relevant for them or not. And so I think it's imperative on us to make sure that our research is understandable so that they can assess whether it's important for them. So I'm just moving stuff around so I can see my slides. Okay. So that's the introduction. So I think of this as a transparency issue, transparency towards our readers. It's important for other methodologists to be able to check our math and assumptions, but it's also important for our readers to be able to assess if what we're telling them is useful and important for them. And I think this is often not the case. And again, this is a meta point that I'm making after having worked on these 3 other issues where there's a lot of excellent work from a technical perspective, but that when I approach it from a practical perspective, I'm not sure that it's useful for the people it's being sold to, so to speak. So to all 3 of them, all 3 of these meta-analysis, random effect models, and Bayes factors, I'm going to be contrasting what the math says and what I intuit researchers actually want to do. So it assumes that the effects we study are drawn at random. And I think when people do experiments, they're very purposely not random. They curate them to be credible or interesting or addressing a specific weakness of prior work. That they come from defined populations. And I think it's hard to define populations, especially for psychology experiments that generally don't exist. That those populations have known distributions, when in fact, if there's no population, there's no distribution. And I'll explain this. It's probably puzzling to people less familiar with psychology experiments. I'll explain what I mean by this in a few moments. But even if those populations were to exist, they will be different for each researcher. And so it's hard to generalize from one study to the population of another researcher. And ultimately, they all assume that what we really want to know is the true average mean effect. And if you think seriously about all of these steps, that effect just doesn't exist. And what people really want to do is get a local effect from an experiment and then use critical thinking to generalize that to other contexts. One way to think is a bit more formally is that there's too many parameters that are not operationalized or measured in any given experiment, and we can use our general knowledge of the world to generalize beyond them, but not with just with the data that is collected. So we'll talk about these three specific projects, and I'll start with mixed models. This is a small portion of a project that I'm doing with Andres Montealegre at Cornell and with Yanis Amangilidis, my colleague at Barcelona. And I'll just focus on a few of the things that I think are most relevant for this audience. So we talk about as a very unique challenge that psychology has in relation to hard and applied sciences, which is that if you're in medicine and you want to know what's the impact of a vaccine, you randomly give people the vaccine and you see if they get COVID or not, and then you have your estimator. And if you want to study from an economics perspective, what happens if I default people into the 401ks? I default people into the 401ks and I see what happens. But in psychology, we ask questions that are like, what is the impact of experiencing disgust or moral judgment? To answer the bigger questions, to what extent is morality a rational process, or is it based on our emotions that are and tinting our rationality? And the problem is that disgust and moral judgments are latent constructs that we have to proxy for in specific experiments. So we may do experiments like this, and this is a lot of experiments that are just like this. We present people with a disgusting stimulus in us, which can be cockroach or fish, that will be a control. And then we ask them about an ambiguous act, and we ask them, is this moral? And we test whether this impacts that. And this is just an inherently more difficult task that it has all sort of challenges. And some of those challenges render the random effect that I'll describe later as, in my view, in our views, as the authors of the paper, not answering the question that researchers are really asking once one considers what they're really interested in. So one way to think about it is that in psychology, when we do psychology experiments, we randomly assign stimuli to participants. So they either see a cockroach or a fish, but we do not randomly assign the attributes to the stimuli. So we don't take something and then randomly make it disgusting. So the stimuli are confounded. And because the stimuli are confounded, the psychology experiments are confounded. So for this, I'm going to give you an example from a 1971 paper that gave rise to, this is the first time most of psychology started worrying about generalizability from specific stimuli to general stimuli. So Rubenstein had an article that were trying to assess how do people search their mind for the meaning of words? How is the lexicon organized? And so they had a particular theory, which is that we sound words out and then search our lexicon through sound. And that made the prediction that if that were the case, then a homophonic word would create conflict and would slow down recognition. So the prediction was that if people were asked to recognize, is this a real word or is that a real word, they would take longer to recognize words that had homophones, because the homophone would be interfering with the retrieval. They would be thinking of prey with an E, and that would slow it down. Now, we can randomly assign people to be phrased with this word or that word, but we cannot randomly assign prey to have a homophone or not. And therefore, the comparison between prey and pest is confounded. So this was recognized, and the solution for this that was proposed, and that psychology embraced and has embraced even more strongly the last 10 years, has been to just use many different stimuli so that all these confounds would cancel out. To give another example of this kind of challenge, with the same cockroach type situation, we want to see if disgust impacts moral judgment. Another common intervention is to randomly assign people to watch a disgusting scene or a non-disgusting scene, in this case, sadness, to control for the negativity of the emotion. So this induces disgust or not, and then we have them do a moral judgment. But the problem is that those inductions are confounded by all these other mechanisms that could lead to it. So even though we have random assignment, and this was alluded to in the earlier talks, even though we have random assignment to the stimuli, we don't have random assignment to the construct of interest. So the way that this has been proposed as a solution started with Clark. Sorry, that's a mistake. That's 1973. Since 1973, with lots of more emphasis on this in the last 10, 15 years, has been to estimate mixed models, where one formally considers any so when first uses multiple stimuli and one models the variation across stimuli in order to extract the true effect of the particular attribute of the stimuli of interest, in this case, disgust. So they say run many stimuli and use mixed models. I'm not sure if the audience is familiar with mixed models. Basically, mixed model it's a regression where you have at some level, for example, the condition, you're in the disgusting condition or in the neutral condition, and then at a different level within the condition we have stimuli, and we model explicitly the variation within the condition, and then separately, in that sense, we're mixing stimuli level variation with condition level variation. And they say nothing about how to choose the stimuli, which we talk about in the paper, and I will not talk about here. Or how do you learn about the validity of your study from the variation? It's just a matter of generalizing from it. So I'm going to skip how we propose choosing stimuli and go straight to the statistical analysis, which I suspect is of more interest to the audience, especially to the meta point about taking math literally versus researchers seriously. Okay, so the advice then is the way to deal with this problem that in psychology stimuli are confounded is to use many stimuli and to then explicitly model the variation across stimuli. And that will solve the problem. And the problem they have in mind is one of external validity or generalizability, where it may be true, so going back a bit, it may be true that people take a shorter amount of time to recognize prey than pest, but that is just for this particular pair of words. If we had chosen a different set of words that were either had homophones or not, we will get a different result. And the solution to that problem in this literature with thousands of citations is select many, many words, model the variation across words, and then you learn whether it's generalizable or not. So what I'm going to do is argue that that solution is expensive from a statistical power perspective, and it doesn't address the question of interest. And for that, I'm going to need a concrete example. For this concrete example, I'm going to rely on a different paradigm that's more common in economics. It's called the endowment effect. And the endowment effect consists of the notion that, I don't know if the audience is familiar, but the endowment effect is the idea that when you're endowed with an item, just because I own it, I value it more. And so it's typically studied by comparing how much I asked. If somebody says, how much will you sell this mug that is yours? I'm randomly assigned the mug in the experiment to be mine. How much would you sell it for? And if you're not assigned the mug, how much will you pay for it? And that difference, which people asking more to sell something than they're willing to pay for it, it's called the endowment effect. So suppose we're going to do an endowment effect study with multiple items to address this problem of stimuli confounded. So maybe there's something specific about the mug. So let's say I use a mug, a pen, or a keyboard. I'm going to be thinking here about the challenges that having multiple items per participant imposes statistically and the solutions. And one of those solutions will be the mixed model with random effects. And I'll do that to emphasize the limitations of the prescription that has become the consensus. And I realize that all three of these are effectively the same, and mixed model is just a regression. But for practical perspective, they're used differently, and different aspects of them are emphasized. And that's the way I will deal with it here as well. So focusing on the challenges, if the same participant is going to tell us how much they would pay for these three items, the first problem we face, again, I alluded before, is that we have the same participant, in this case, symbolized by Richard Thaler. If Richard Thaler is telling us how much he would pay for this, and for that, those three observations are dependent. If Richard Thaler has a lot of money for winning a Nobel Prize, for example, he may be willing to pay for all three items more than somebody else who did not win the Nobel Prize. So if you're doing a simple analysis like a t-test, the one way to deal with dependence is to simply aggregate the data and just ask how much is Richard willing to pay for all three items, and that eliminates dependence because now we have just one observation per Richard. If you do a regression, you can do that by clustering the standard errors. And if you do a mixed model, you can do what's called a subject random effect, which you estimate a distribution of how valuation in general items varies across people. So we don't need mixed models to deal with dependence. We can deal with it very easily here. Another challenge rather, is variation across stimuli. Pencils are cheaper than mugs, are cheaper than keyboard. If we therefore run a study with three items instead of just one, we add noise to our experiment, making it harder to detect any effects. With a t-test, if we analyze data at the subject level, they cancel out, so it doesn't matter. In a regression, we can do stimuli fixed effects. In a mixed model, we can do stimuli random intercepts. So also for this challenge, we don't need a mixed model. What do we need a mixed model for, and why is it advocated for so strongly in psychology? To generalize. Okay, so to generalize to other stimuli. How can we generalize to other stimuli? So we didn't have here a lamp or a trip to the Costa Brava. We didn't have those items. So how do we know if they generalize those other items? With a t-test, the researcher has to think about it. They have to think, to what extent can I generalize from these 3 items to others? With a regression, the researcher has to think about it. But with a mixed model, we can engage in something that we referred in a non-derogatory way. We think it's a descriptive term as Platonic generalizability, and then this issue is also addressed purely statistically. Okay, so what is Platonic generalizability? And this goes back to how I was motivated to talk early on about assumptions we make that are mathematically elegant. We assume there's a population of all possible stimuli. For example, all the goods that exist in the world and all the goods that could, we can ask people to imagine. We can easily run on a study asking people how much they would pay to travel in time or to have dinner with a famous person, even if that's not a real good. Now we average them. That's easy to do with something where true populations exist, like people, about half people are men, half people are women. But it's hard to do for the endowment effect. Like if the effect is different for some goods and for others, we need to decide what percentage of all items out there in the world that we could run experiments for are mugs versus a dinner, Obama dinners, right? Having dinner with the Obamas versus a particular phone. So we assume, okay, we assign some weights there and we compute that population effect size. That's what we're trying to estimate. Then we assume that researchers choose those stimuli at random. And we assume that researchers want to generalize. They run their study so they could generalize to this, to that weighted average of all of them. And because we believe, or we argue, that this average does not exist, we argue that what the mixed model is providing is a Platonic generalization, right? It's taking this one study with keyboards, mugs, and pencils, and generalizing to this Platonic mean of all possible items you could use in an experiment. That could be, if that were free to do, to say, well, let's just generalize to some, loosely speaking, a lot of authors says, well, don't take the random effects assumption literally. Take it as a sense of the set of items on which people could have drawn the experiment, some more local generalizability. If it were free to do it, maybe we would do it, but it's expensive. And this is the kind of trade-off that we believe readers should be aware of when they're presented with different methodology. So I'm going to show you simulations of what would happen if you analyze experiments like the one I described with the endowment effect with the different tools, the t-test, the regression, or the mixed models. Okay, so if subjects, here it matters whether every participant sees all of them or not, but I'm going to skip over some of those details. Here I'm going to have simulations where participants see 2 items, keyboards and pencils, 5, 10, or 25 different items. And we analyze the data with just a t-test with regression or mixed models. And then here I focus on what are you addressing? Only dependence, or also controlling for stimuli variation with the fixed effects, or this Platonic generalizability, which is the main reason why psychologists have been told to run random mixed effects. So this is the power, this is the probability of detecting that overall items people ask for more money to sell an item that they're willing to pay for it. Obviously, we need to make a lot of assumptions to run, or operationalizations to run these simulations. But in our supplement, we have very many variations showing that these are not dependent at all on this particular assumption. These are general patterns. And the general pattern, and they're somewhat easy to intuit, is that power is the same for all the tools except for Platonic generalization. Now that's true whether you have 2, 5, 10, or 25 items, okay? So from our perspective, what's happening is, this is what methodologists have been recommending to psychologists, the red bar. And all the simpler analysis are not recommended. They're said, this is primitive, this is incorrect, we should leave this behind. And why is this being sold? Why is the red bar being sold? Because it offers Platonic generalizability. It offers researchers to go from the stimuli they run to the stimuli they could have run. And I'm going to skip the results for if you were using a subset of them, okay? Now, the people who advocate for this in those methodology papers, they know about the lower power. They are aware of it, and they don't care. And therefore, they don't warn their readers about it. They don't warn their readers about it because they worry that if you don't run a mixed model, you have too many false positives. The t-test and the regression are wrong in a statistical validity sense. And we definitely care about false positives, right? My most famous paper has false positive in the title. I care about it. We care about it. But we don't care about those false positives. We don't care about the false positives that methodologists have used to recommend this particular tool to psychologists. And the reason we don't care about it is that we think they are true positives. We don't think they should be classified as false positives. This can be pretty philosophical and obscure, but I think a concrete example will help. And if I lost you at some point, this is, I think, the most important figure of my talk. Okay, so this is the time to get back from your email client. This is the way we take the math literally. This is the way we think about a psychology experiment. There's a distribution out there of possible effects. Okay, and let's say this one is centered on 0 because it will be useful for the false positive argument. The true average effect, let's say of the disgusting versus no disgusting stimulus, on average is 0 in terms of the morality. Okay, so if I were to choose at random from this hypothetical population of all possible disgusting things, the average effect on morality judgment would be 0. However, on any given experiment, if I run few stimuli, let's say I run just 6 stimuli, the average of those 6 stimuli is not 0, it's positive, it's around here. And so if I run enough participants, that mean will be not 0, will be positive, and it will be statistically significant. And that is what the advocates for mixed models worry about. This is the reason they are willing to accept the lower power of the mixed model, because the mixed model estimates that distribution, and on average, it gets it right. So if you were to run a mixed model here and model this distribution, even if you have just 6, on average, you will reject the null of a 0 effect only 5% of the time. While if you run a t-test, because on average for those 6 stimuli, it's over here, and you don't adjust for the fact that those 6 stimuli are drawn at random from other stimuli, you do over-reject, quote unquote. Why do we think that's okay? Because this is taking the math too seriously. Too literally. Let's take these researchers more seriously. This is probably how a psychologist would think of the population of stimuli, okay? So again, let's think all these different effects come from different disgusting stimuli. Why would you get a negative effect? Why would seeing something disgusting make something seem less immoral? Well, one possibility is a contrast effect, right? So compared to barbecuing organs, having incest seems less severe. And so if people are presented with this extreme case, then it reverses in the other direction. Or maybe some extreme form of immoral sexual act will also have a negative effect. But the researcher thinks these are not of interest to me. These are confounded, so I'm not interested in them. And then there are other effects that are just too subtle, so they would never run the experiment for them. And some other effects that the IRB, they wouldn't allow them to run the study. So the blue region is the one they care about. And those two effects, S4 and S5 that they run, those are true positives. Those are true effects that are true positive in the sense that if somebody else were to look at their paper and decide to rerun those studies, those two effects will reproduce and will generate the same conclusion. And if we think about, okay, those are the two, in what proportion are there? Maybe can we redefine the random sampling to mean only from the blue region if we wanted to do that? How many true, and I'll have to move this, how many true studies are out there in the population, the Platonic universe, that involve watching a man clip his nails and watching a train sporting scene? That is a meaningless question. There's no relative frequency of these two different stimuli. So there's no true mean here that we're trying to estimate. What we're trying to really do is say, can I find stimuli that I could believe are valid and that are replicable? And from that, I generalize using critical thinking. Okay, so that was the first one. I'm going to skip this, given my perceived interest of the audience. I'll focus more on the last point, which is on Bayes factors. So I'm going to skip as well the meta-analysis, which I was expecting to skip, and then I'll get
You have 5 minutes.
Yeah, that's perfect. So I'm going to make a very similar argument for a possible disconnect between how methodologists have thought about research questions and how researchers think about research questions. So with Bayes factor, I wrote 3 blog posts on this, and I submitted this as a paper. I had 3 Bayesian advocates as reviewers, and decided that this would best live as blog post without having to deal with a review process. Okay, so if those interested, you can just visit Data Colada 78 and they will read it. I also got the second one, which makes the most important point in my mind for today's theme. So the way the Bayes factors start, we can think of the likelihood function. So let's just start with the normal, right? If we ask if the true effect were 0, what would we expect to observe across different studies? That's just the distribution center around 0. And we can ask for the likelihoods if the true effect were 0.5, a quantity of 0.5, so half a standard deviation difference between means. And that is the likelihood for if the true effect were 0, this is the likelihood if the true effect were 0.5. And so one can look at that ratio, look at the likelihood ratio between them and say, oh, this effect I obtain is 21 times more likely if d equals 0.5 versus d equals 0. And we can use that in some way or another to update our beliefs or make conclusions or make decisions, whichever type of situation we're in. And we can then consider, well, why only consider 0.5? We consider what if the effect were larger? So if the true effect were 0.8, it would be 7 times more likely we would see 0.5 than if the true effect were 0, and so on for these other ones. And this one is naturally 1 because it's comparing 0 to itself. So that's all fine. This is I'm basically going step by step into a Bayes factor from likelihoods. Let's go beyond just those 3 small, 3 sort of default sizes to all possible effects between 1, -1, and 1. And this gives us a curve, the distribution of the ratios. This is again, if the truth were 0.5, it would be 21 times more likely we would see the data that we saw than if the truth were 0, it would be 7 times the same numbers as before. Now, here are my claims. I am quite confident I would say, that research will be interested in this chart. It's not often presented in papers, and it seems likely that researchers would be interested in it. I am semi-confident that they could be persuaded that actually all the information they would extract from this curve is already contained in a confidence interval. I would bet a small amount of money that that's true, that once you convince them this is useful, and then you can trust what they actually do with it, they would say a confidence interval, it's about the
2
same.
minutes.
Perfect. But what I'm most confident of, and what is most interesting, is that nobody would want to do the following, which is to say, let's take an average of all these numbers to summarize it into a single number. And they definitely wouldn't want to use arbitrary weights for that, which would be say, let's just give all these possible numbers and weight that's proportional to a normal 0.71. And that's what a Bayes factor does. Right? So we can give a lot of very in-depth philosophical arguments for how to treat evidence one way or the other. But if we describe the steps of what are happening, my claims are that researchers would say, I don't want this. I don't want to average those likelihoods ratios into a single number based on these arbitrary weights. Okay. So to close, this is my last slide. I'm gonna critique, since I'm used to having audience questions, and I'm gonna challenge my own presentation. Here are shortcomings to my argument. One is that I'm equating my own intuition about what researchers do with what they would say if we were taking them seriously. It's possible that psychologists run studies for reasons that are different than the ones I intuit, right? It's convenient for me to believe that. And it's certainly possible that I'm wrong, right? This is, like this was here, has to talk about the statistician's fallacy. Could be that I'm saying I know what they want to ask and I'm wrong about it. It's also possible that if one could make the kind of common sense arguments I made against mixed models and against Bayes factors, against other things that I do like p-values and the stimuli plot that I skipped over, which are alternatives to the mixed model. But that's okay. That's okay. We can have those arguments. We can have the argument. Is that really what researchers want, or are the common sense argument against p-values that resonate with researchers? The meta point I'm trying to make to this conference is we need to make arguments in ways that real researchers can be the jury for them, right? So if these methods are not silly, somebody should counter-argue in a way that resonates with the research, in a way that they can say, not if this is theoretically or philosophically correct, but if it speaks to the question if it speaks to the question they have in mind. If you have reactions, that's the email where you can send me your complaints.